Well, in today's lecture, we are going to learn about the reaction mechanism. So here, the reaction means that is nothing but the conversion of reactant into product that we call reaction. And the meaning of mechanism here, that is nothing but the step-by-step conversion of reactant into product that we called mechanism. So reaction mechanism. Well, so the different kinds of or different types of reactions we already learned in previous semesters, that are addition reaction, elimination reaction, substitution reactions. Yes, these are the main types of reaction mechanism. So other than this, we come across the conversions as well, the rearrangement reactions. So most of in today's lecture, we are going to learn about the rearrangement reactions. So here, the rearrangement is nothing but the migration or the movement of the group or atom from one atom to another in a molecule. So rearrangement is nothing but here. Rearrangement here is nothing but the migration or movement of group or atom from one atom to another in a molecule. So that we call rearrangement reactions. So in rearrangement reactions, we come across mainly two types of rearrangement reactions. One is the intermolecular rearrangement reaction. Second one is intramolecular rearrangement reactions. So rearrangement is nothing but the movement of group or atom from one atom to another in a molecule. So that we call rearrangement. So again we come across two types, intermolecular rearrangement and intramolecular rearrangement. So intermolecular rearrangement is nothing but the movement of group or atom takes place in between two molecules that we call intermolecular rearrangement reactions. The movement of group or atom takes place in between two different molecules that we call intermolecular rearrangement reactions. And intramolecular rearrangement reactions is nothing but the movement of group or atom takes place within a molecule that we call intramolecular rearrangement reactions. In this unit, we are going to learn about that is the intramolecular rearrangement reactions. So some of we follows, that is first one, that is the Beckmann rearrangement reactions. So here Beckmann is nothing but it is the name of scientist. So in previous semesters we already learned different kinds of reactions. That means the name given to particular reactions that depend on the name of the scientist. He particularly studied that reactions. So on that basis also they given the name for that particular reactions. As well, the name given to particular reaction that depend on the reactant name and the product name. On that basis also they give the name for the particular reactions. So here, so we are learning the reactions that are mainly a named rearrangement reactions. That name came from the scientist name. So that scientist, he studied particularly that reactions. The first one, that is the Beckmann rearrangement reactions. Beckmann rearrangement reaction is nothing but the rearrangement of ketoxines into N-substituted amides catalyzed by a different acids. Yes, so Beckmann rearrangement reactions is nothing but rearrangement of ketoxines into N-substituted amides. So in the presence of different acid catalyst. So here the meaning of catalyst is nothing but, so some of the molecules, or that is the acid molecules, they helps to convert reactant into product without change in their chemical nature. So that we call catalyst. So the difference between catalyst and reagent, reagents also helps to convert reactant into product. That means the reagent and catalyst, they increases the rate of the reaction. Yes, So their reagent that helps to convert the reactant into product with change in their chemical nature, but here catalyst they helps to convert reactant into product without change in their chemical nature. So Beckmann rearrangement reactions is nothing but the rearrangement of ketoxams into N-substituted amides. So in the presence of acid catalyst. So that acid catalyst are H2SO4, SOCl2, PCl5. That is sulfuric acid, sulfuryl chloride or thionyl chloride we called, or phosphorus pentachloride. Yes, H2SO4, SOCl2 and PCl5. So these are the acid catalyst we used in a particular Beckmann rearrangement reactions. So here the ketoxams is formed by the nucleophilic condensation reactions between ketone and hydroxylamine. So here ketoxams are formed by the condensation between the ketones and hydroxylamine. Hydroxylamine is nothing but NH2OH. So condensation reaction is nothing but the joining of two molecules into one by the elimination of some byproducts. So here joining of the ketone and hydroxylamine takes place by the elimination of what? Water molecule. So that we call condensation. That is the nucleophilic condensation of the ketone and hydroxylamine. That gives the ketoxams. The rearrangement involves the migration of a group from carbon to electron deficient N center or N atom. So here the rearrangement involves the migration of group from carbon to electron deficient N atom. So that is, so this is the ketoxams that involve the reaction, that means conversion of ketoxams into an N substituted amide. That is why the migration of particular group or atom from carbon to the deficient N atom. Yes. So it is found that the migrating group is anti to the hydroxyl group. So here we seen the structure of ketoxam. Ketoxam I written here at one corner. So that is because of, so this nitrogen atom that have the lone pair of electron. So this hydroxyl group that is present at one corner, that is because of there is a repulsion between lone pair and bond pair, so that it is present at one particular corner. So the migration that takes place, that is to the anti, or the movement of group from the carbon atom that takes place to an anti to this hydroxyl group, that we can see at the second molecule. So here that involves the exchange of the R dash and hydroxyl group. That is the meaning of here. It is found that the migrating group is anti to the hydroxyl group. The migration that takes place in a molecule, so that group is the opposite to this hydroxyl group. So I taken here the general molecule or general reactant molecule, that is the ketoxams. So here hydroxyl group opposite to that is an R dash I written. So in the second molecule we can see in here the exchange of the molecule takes place. That means the migration of R dash that takes place to the nitrogen atom, that is anti to the hydroxyl group. Anti, or that also we call opposite or transposition to that hydroxyl group. So the migration of group from the carbon atom that takes place, that is an anti to the hydroxyl group. Yes. So the mechanism we can see in here. So this Beckmann rearrangement reactions that takes place, so in the presence of acid catalyst. Yes, ketoxam in presence of particular acid here. So we have taken the H2SO4. So acid catalyst in a solution that gives a protonic ion concentration. Yes, hydroxylamine in the presence of H plus. Then the H plus that attack on hydroxyl group. The H plus that attack on hydroxyl group. The second molecule we can written here the OH2 plus. Yes, after attacking H plus on the oxygen group, the OH convert into an OH2. The plus charge is because of oxygen loses its one of the lone pair of electron. Then the next step, the removal of water molecule takes place. That is because this oxygen re-gets its lone pair of electron. So the removal of water molecule takes place, so that by the removal of water molecule N gets positive charge. That is because oxygen takes bonding electron towards itself and eliminate as a H2O. So after eliminating H2O, the N gets the positive charge. Here this nitrogen is electron deficient center. At this position, the migration of the group takes place from the carbon atom. So in the second or in the next step we written here, after migrating this R group to an nitrogen, yes, the carbon gets the positive charge because the R eliminate as a R minus towards the nitrogen, so that carbon gets the positive charge. So positive charge carbon we call carbocation. Then to this carbocation, the attack of the water molecule takes place. So already eliminated water molecule already present in the solution mixture, so that water only attack on this carbon atom. That is because of this carbon is presently at a electron deficient center. So water molecule attack on carbon atom. So here the bonding takes place with what in between water molecule and carbon atom. So that written in this step. So from this step to this step, the elimination of the hydrogen takes place. The elimination of hydrogen takes place. That is because of oxygen, after sharing its lone pair of electron with carbon atom, oxygen loses its one of the lone pair of electron. So that lone pair of electron oxygen re-gets from the hydrogen bonding. So that with the elimination of H plus, the next step we written here, that is COH R C N double bond N R dash. Yes. So from this step to this step, it is a these two are in equilibrium. That we called the conversion of the hydroxyl product into an carbonyl product, that is by the enol ketotautomerism. So here it involved the tautomerism, that is the enol ketone tautomerism. That is by the migration of hydrogen from OH to the nitrogen. So from this molecule to the next, what the product converted is, that is the amide. So nitrogen R dash, the hydrogen that is transfer from this oxygen to nitrogen, so that convert NH, that is by this bond transfer, or this bond that goes into between oxygen and carbon, then this double bond in between carbon and nitrogen that sits on nitrogen, and the hydrogen eliminated as H plus, that bond or that form bonding with nitrogen, so that this molecule converted into an amide, or the hydroxyl substituted imine converted into amide by the tautomerism, that is enol keto tautomerism. So this is Beckmann rearrangement reactions. The name Beckmann is because of this particular rearrangement reactions is studied by the scientist Ernst Beckmann. Migrating group retains its configuration that indicates that migrating group does not become completely free during migration. The migrating and NO bond breaking takes place, that is very fast. So this means the migrating groups, it retains its configuration, that is because of the migration and breaking of NO bond, the migration of the R group from carbon atom and breaking of the NO bond are very fast, so that the migrating group retain its configuration. So some of the application of this Beckmann rearrangement reactions are, so in the synthesis of isoquinoline from cinnamaldehyde that involved the Beckmann rearrangement reactions. That means the conversion of isoquinoline into an cinnamaldehyde. So that convert through the Beckmann rearrangement reactions. So that it is one of the application that we can see in conversion of isoquinoline to an quinoline into an cinnamaldehyde. Then second application is in the synthesis of lactam. So lactams are nothing but cyclic ketone molecules. So E-caprolactam formed by Beckmann rearrangement reaction that has application in nylon manufacture. Yes. The third application is in synthesis of paracetamol. So paracetamol synthesis that is also involved the intermediate Beckmann rearrangement reactions. So these three are the applications of Beckmann rearrangement reaction. That is, first one is in conversion of isoquinoline into cinnamaldehyde that involved Beckmann rearrangement reactions, and in the synthesis of lactam. So particularly caprolactam that is used in nylon manufacture. Yes. And the third application is in the synthesis of paracetamol also involved the Beckmann rearrangement reactions. So this is about Beckmann rearrangement reactions. Next rearrangement reactions is Puresky rearrangement reactions. So here this is also a named reaction that Puresky is nothing but the name of the scientist, that is Alexei Puresky, and Russian chemist. He studied particular this rearrangement reactions, so that the name Puresky rearrangement reactions. So here Puresky rearrangement reactions is nothing but the rearrangement of alpha halo alkanes into ester. So with rearrangement carbon skeleton in presence of alkaloid ion. Yes, this is known as Puresky rearrangement reactions. So Puresky rearrangement reactions is nothing but the rearrangement of alpha halo alkenes into an esters in the presence of alkoxide ion. So this alkoxide ion that may be a sodium alkoxide ion. So here we can see the reaction, that is alpha haloketones converting into an ester. Yes, that is in the presence of alkoxide. So that is a sodium ethoxide as a reagent. Yes. So here alpha haloketones is because of the halogen that is present to the carbonyl group on a carbon atom, that is alpha to the carbonyl group. So that is the name alpha haloketones. So Puresky rearrangement is nothing but alpha haloketones, the conversion of alpha haloketones into esters in the presence of sodium ethoxide ion. So mechanism, the rearrangement takes place through the formation of carbon ion and by 1,3 elimination forming cyclopropane intermediate. So this rearrangement that takes place through the formation of carbon ion. So that carbon ion formed cyclopropane through the 1,3 elimination as an intermediate cyclopropane molecule. So the cyclic intermediate is further attacked by base. So that is nothing but this molecule only, that is a ethoxide ion. Yes, the cyclic intermediate is further attacked by base followed by ring opening gives another stable carbon ion. So that mechanism we can see in here. So here the exchange of proton in this carbon ion gives the final product. So the cyclic intermediate after the attack of base that gives a second stable carbon ion. So that carbon ion exchange of proton takes place and that gives the final product. So this is the mechanism alpha haloketones. So in the presence of base ethoxide ion. So this base that helps to eliminate acidic proton. So acidic protons are the proton that is present on carbon atom, that is alpha to the carbonyl group. So these are acidic in nature, so that the elimination of these proton takes place very easily. So this ethoxide ion that abstract this proton, so that gives the carbon ion. So this carbon ion that attack on this carbon atom, the elimination of chlorine takes place. So this chlorine, the sodium already present in the solution, so that eliminate as a sodium chloride. So by the attack of this carbon ion on this carbon atom, the elimination of Cl takes place. At the same time, it gives intermediate cyclopropane. This is a cyclopropane. So this is intermediate cyclopropane molecule, that is by 1,3 elimination. So here the 1,3 elimination, that is nothing but 1, 2, 3. 1, 2, 3. So it involved 1,3 elimination, that is the elimination of chlorine from this carbon atom and elimination of hydrogen from this carbon atom. So that we called 1,3 elimination. The result of 1,3 elimination that gives an intermediate cyclopropane molecule. So at this stage, the cyclopropane molecule is attacked by the base molecule, that is the ethoxide ion. So this ethoxide ion that attack on this carbon group. So after ethoxide ion attack on cyclopropane, that gives the next product, that is oxygen ion intermediate molecule. So the intermediate molecules that not have particular names. So oxygen anion intermediate molecule. So this oxygen anion intermediate molecule, further resonance takes place and the cleavage of, after resonance, the cleavage of this cyclopropane takes place. So that results the formation of second carbon ion. Yes, after resonance of this oxygen anion and the breaking of carbon-carbon bond takes place. So after breaking of carbon-carbon bond takes place, the breaking of cyclopropane takes place and the formation of the second carbon ion, that results this molecule. Yes, so the hydrogen, that is H plus, already present in the solution, that hydrogen is from the first reactant molecule. So here this ethoxide ion that helps to eliminate this proton as a H plus, and secondly that ethoxide ion only that attack on the cyclopropane. The left behind what we had in the reaction mixture, that is a H plus. At this stage that H plus attack on this carbon ion. Yes, this H plus that attack on this carbon ion, that results the formation of the final product, that is the ester. So that ester is nothing but 3-phenyl ethyl propanate. So this is the reaction mechanism. Alpha haloketones in the presence of ethoxide ion. So ethoxide ion that helps to eliminate H plus, that results the formation of carbon ion. So this carbon ion attack on this carbon atom with the elimination of this Cl. So this Cl and already present the Na plus in the reaction mixture. So the elimination of NaCl takes place, that results the cyclopropane, that we called 1,3 elimination. So on cyclopropane, the attack of alkoxide ion takes place, that results the oxygen anion intermediate molecule. So this oxygen anion intermediate molecule, after resonance, the cleavage of cyclopropane takes place, and that gives the second carbon ion intermediate molecule. So this second carbon ion intermediate molecule, after reacting with H plus, that H plus already present in the reaction mixture, that gives the final product ester. So that is the 3-penyl ethyl propanoate. So this is a Puresky rearrangement reactions. So Puresky rearrangement reactions is nothing but the rearrangement of alpha haloketones into an ester in the presence of alkoxide reagent. So here the alkoxide that act as a reagent, that is because it helps to convert the reactant into a product with a change in their chemical nature. So sodium ethoxide that involved in the reaction, that gives the final product, that is the ethyl ester. Yes. So in the previous rearrangement reactions, there we seen the acids, they act as an catalyst. So here ethoxide that act as an reagent. So that is the difference between the reagent and the catalyst. So some of the applications of the Puresky rearrangement reactions is, that is, first one, in the presence of in the preparation of carboxylic acids. So instead of using sodium ethoxide, if we used sodium hydroxide, the final product is the carboxylic acid. So that means one of the application of Puresky rearrangement reactions is we can convert alpha haloketones into an carboxylic acids. So in the presence of reagent, that is sodium hydroxide. That is the first application. Second application is in the preparation of ester. So this particular example we seen, that is the alpha haloketones into an ester. So this is a second application. Third one is in the preparation of amides. So these are the three applications of Puresky rearrangement reactions.